I wanted to share with you one of my favorite theorems, which combines geometry and number theory. Geometry is roughly the study of shapes, angles, areas, and volumes, while number theory is the study of integers, primes, Diophantine equations, etc. How would we possibly go about fitting these two disciplines together? We could consider the real number line and study the geometry of integer points on it. However, the unfortunate thing here is that one-dimensional geometry isn't very interesting. Instead, let's look at the Cartesian plane, where each point has two real number coordinates. Points of importance to us are those with integer coordinates on both directions. From now on, let's call these points, what's a creative name for them? Let's call them integer points. Now that we have a plane, we can consider shapes on it and analyze the relationship between the geometry of shapes and integer points. Consider a circle, for instance. Does it contain any integer points? How about now? Now, you can see that whether or not the circle contains any integer points depends on two factors: where it is centered and how long a radius it has. Let's place the center of the circle at the origin and ask the same question, but with a slight modification. Instead of integer points, we're asking if the circle has any non-zero integer points. How does the radius affect the answer to this? If you said that if the radius is greater than 1, then the circle contains some non-zero integer point, then you're right. We can replace the circle with any other shape, say a square, and ask the same question. In order to analyze this question for a whole class of shapes, we must impose some restrictions on what these shapes can be. The shapes we're looking at we'll call symmetric convex bodies, and if M is a symmetric convex body, then it has the following four properties. 1. M has to be bounded, meaning you could draw a large circle that contains M. So things like polygons are bounded, while lines or even the entire plane are not. Number 2, M has to be open, meaning the boundary of M is not a part of M. That is, if an integer point happens to be on the boundary of M, then we won't consider that as a point in M. Number 3, M has to be convex. That means that any segment with endpoints in M will lie completely in M. For instance, the square is convex, while a shape like this is not. And lastly, M has to be symmetric with respect to the origin. That means that reflecting a point in M about the origin should land you at another point in M. Note how the triangle or the pentagon are not symmetric, while a circle or a regular hexagon would be. Being symmetric means that if you change the signs of coordinates of a point in M, the resulting point will also be in M. We will show how the area of symmetric convex body relates to the question of said body containing non-zero integer points. But first, we'll need to look at another, perhaps simpler and more general result. If we have a set M that is bounded and open, note how we're not requiring convexity or symmetry, with area greater than 1, then there exist 2 points such that their difference is a non-zero integer point. By difference, we mean what happens when you subtract the coordinates of one point from the coordinates of the other, entry-wise. You can of course think about this difference in terms of vectors. What happens when you place the negative y vector on the tip of the x vector? Do you land at an integer point? To show that such a pair exists, let's tile the plane with squares of side length 1. Notice that a pair of points in M, whose difference is an integer point, exists if and only if there are 2 points that have the same location relative to the small square they sit in. So let's take a look at the individual squares that contain some portion of M. Since M is bounded, there's only a finite number of such squares. Imagine taking these square tiles and placing them on top of each other. Since the area of M is greater than 1, thus greater than the area of a single tile, we must have that there is some overlap when we place the tiles on top of each other. Therefore, there exist 2 points in M with the desired property of integer point difference. Now that we have our auxiliary result, we'll try to make sense of the main theorem. This is called Minkowski's theorem. The result states that if we have a symmetric convex body M of area greater than 2 squared, then there is a non-zero integer point in M. This therefore answers our initial question, albeit for a specific class of shapes. Let's prove this. Say that we have a symmetric convex body M with area greater than 4. We'll shrink M by a factor of 2 on both dimensions. The resulting figure will have area greater than 1. Since we're scaling down by 2 in both dimensions, that means that areas get scaled down by a factor of 4. By our lemma, there are 2 points, x and y, such that their difference is a non-zero integer point. Revert back to the original scale and notice that the points 2x and 2y are in M. Since M is symmetric, we have that minus 2y is also in M. We know that x minus y is a non-zero integer point. But could we interpret it geometrically? We're in luck. Since the midpoint between a and b is a plus b over 2, we can interpret x minus y as the midpoint between 2x and minus 2y. 2x and minus 2y are in M, and since M is convex, we must have that their midpoint is in M. Thus, we've cooked up a non-zero integer point in M, and hence proven the theorem. We could stop here, but as it is often the case in math, solving one problem opens more avenues for new questions. What if instead of integer points, we were looking at points on some other grid? Like this, for instance. Those of you who have seen linear transformations before will recognize that this is the image of the integer grid when we apply some linear transformation A to it. Minkowski's theorem is adjusted accordingly as follows. Now we require the area of the symmetric convex body to be greater than 2 squared times the absolute value of the determinant of A. Notice that this makes sense since the absolute value of the determinant of A is the factor by which areas are scaled when the linear transformation is applied. Keep this result in mind, as it is going to be helpful in one of my favorite applications of Minkowski's geometry of numbers theorem. We will use the tools we developed to prove the so-called Fermat's Christmas theorem, or Fermat's two-square theorem. This result claims that all prime numbers of the form 4k plus 1, that is, primes that leave a remainder of 1 when divided by 4, so primes like 5, 13, and 29, can be expressed as the sum of two squares. This is quite significant, as it can be shown that primes of the form 4k plus 3 cannot be written as sums of two squares. Try convincing yourself that that's the case. Back to Fermat's Christmas theorem. How would we possibly go about showing such a property? One way to think about sums of squares is to think about distances. The Pythagorean theorem tells us that the sum of squares of components of coordinates of a point is the square root of the distance from the origin to that point. So for any p of the form 4k plus 1, we're looking to find some integer point such that it is square root of p away from the origin. To do this, we'll need the following fact, which I won't prove here as it is not central to our task, but you can find a proof in the description. For p of the form 4k plus 1, we know that there exists some integer u such that p divides u squared plus 1. Now consider the linear transformation given by the matrix A. A may look a bit arbitrary, but notice that its determinant is p and A sends the point xy to px plus uyy. The reason we've picked this particular u is so that the sum of squares of px plus uy and y is a multiple of p when x and y are integers. So A sends integer points to integer points whose sum of squares is a multiple of p. So we've linked a sum of squares to some multiple of p. However, our goal is to show that p itself is a sum of squares. In our transformed plane, consider a circle M centered at the origin with radius square root of 2p. The area of M is pi times 2p, which is greater than 4 times the determinant of A. Using the theorem above, we have that there is a point on the grid that lies in M. Let that point be AB. Since AB is on the grid, we know that P divides A squared plus B squared, and since AB is in the circle, it means that A squared plus B squared is less than 2P. There's only one positive multiple of P less than 2P, and that is P itself. Therefore, we must have that A squared plus B squared is P, which completes our proof. I'll wrap this video now, but I'll leave you with some things to think about until my next video, which will hopefully come out soon. Can you generalize Minkowski's theorem to higher dimensions? How big a volume do you need in 3 or even n dimensions to guarantee an integer point in a symmetric convex body? Or another question is, could you possibly show that every positive integer can be expressed as the sum of 4 squares using what we've seen today, but in more generality? And lastly, think about a line passing through the origin. Can you choose an angle for it so that it never gets close to an integer point? Say, it doesn't get any closer than 1/1,000,000. I'll answer all of these next time, so be on the lookout for a new video, but until then, happy problem solving.